Okay, I will go. Well, thanks everybody for taking the time to sit in on this talk. As Erica mentioned, my name is Albert Larson. Title of the presentation is Flux to Flow. Today's date is February 21st. Quick background on me. My education is entirely from the University of Rhode Island. I have a master's in business administration, a bachelor's in mechanical engineering, and then a PhD in civil and environmental engineering. Between the bachelor's and grad school, I had about a 10-year gap where I worked mostly in technical marketing. I completed my PhD last May, and now I'm currently at Brown University as well as a research associate and as an adjunct faculty at the community college. I'm married, I have a dog and a cat, and we're expecting our first child in May. It's a girl, the sex is a girl. I like to read, hike, play music. I think there was something else, but I deleted it. And this is a picture of me in my postdoc in May after graduating. So a little bit about me. Okay, so the plan for today is pretty much what I'm going to try to do is drop y'all into the third chapter of my dissertation. If you've read the published first chapter, that's cool. If you haven't, I would invite you to do that. One of the things that you'll find that unifies the work is that I published all of the code alongside of the writings, and I found that was like super duper important because there was I found to be a pretty heavy lift as far as the programming element. So for what it's worth, if you go and pick up the MDPI water paper, you'll find hydrology paper. So anyways, chapter 3, holistic water cycle analysis via the coupling of climate model, satellite ground truth, and machine learning signal processing technologies. And it's a case study of 2 North American transboundary river watersheds. Okay, so the motivation behind the work always keep it crucial to me and to guide the research, right? As a community college adjunct faculty professor, it's always about getting into the questions and what is it that's guiding what we're doing, and I try to hold on to that. I held on to that when I was selling stuff and through my research. So as I was mentioning to Praz, land and ocean observations of water typically aren't coupled by default. Oceanographers like to study the ocean. That's what they focus on. Hydrologists, which I would probably more be called, tend to focus on the land. That is not 100% of the time the truth. Certainly there are folks that consider both, but generally speaking, there are silos. Furthermore, the motivation, considering drought propagation studies, they consider a longer time frame. This study considers a slightly longer time frame. And then one of the things that we know is that slower moving behavior of the climate, like El Nino and La Nina, as one example, are witnessed in sea surface temperature, right? So water has a high heat capacity. Slow moving phenomena tend to be present in our satellite observations of the ocean. So, okay, with that, what are the essential research questions? There's the motivation, that high level stuff, but then the details are, what's the impact of when we actually merge ocean and land surface observations of the water cycle on stream flow prediction, right? So I am a hydrologist. Flux to flow is all about taking observations of water and using them to predict the flow of rivers. And then, okay, knowing that I was using a neural network approach, how does increasing and decreasing the number of output targets, so the number of streamflow gauges, impact the performance of the neural network? And then how do simple neural networks fare in the prediction of streamflow as compared to those that are a little bit more complicated? Okay, so the data sources that I used GLDAS, I used MODIS, I used streamflow gauges from the USGS and from the Canadian Water Office. For those of y'all who don't know, GLDAS, that means the Global Land Data Assimilation System. It is an initiative that is run by NASA at Goddard. where there were a few organizations that got together, used a common set of meteorological forcings, put them through three different water and energy budget algorithms, and got a number of outputs, 31 outputs. I used 2 of them, which I'll show you, I think, in the next slide or 2 slides later. That covers the land. MODIS, that covers the ocean. I used an L3 product, the thermal monthly 9 kilometer resolution nighttime data set. Okay, yeah, it's I'll show you the GLDAS in a couple slides. This slide just shows you the extent of what we're studying, right? So the Yukon Basin, transboundary, right? The US into Canada, and then the Columbia Basin, again, the US into Canada. The Yukon, I looked at 6 basins. The Columbia, I looked at 7 basins. It was really constrained by what was available at the time. You're looking for we need a time series, right? So at the time we needed a time series. So continuous data. I looked at, what was it, about 18 years. So really it was relatively sparse when I was going out and looking for that time series data, but this is what I found. This is the essentially the target, what we're trying to predict, all at the same time, right? So I take some kind of image as an input through the neural network, and we get either the 6 or the 7 streamflow outputs. Okay, so talking about the imagery, right? So talking about GLDAS, the Global Land Data Assimilation System. It has those 31 outputs. We're interested in water and how it moves across the land and throughout the environment. So what we grabbed was, surface and subsurface flow, right? QS in this first panel right here is going to be surface flow, right? So as the rain falls from the sky, it hits the land and it either infiltrates or it runs across the surface. So that would be the surface flow of water. Again, this is computationally found from the meteorological forcings. If you look on the right top row, you'd see subsurface flow. So quantified what happens to the water after it rains and if it's able to percolate into the ground. That covers the top row. Second row, I put those 2 together. I just put those 2 together. What you see is there's all that white. That's where the ocean is. Those are NANs, right? So the Global Land Data Assimilation System, it doesn't say the Global Data Assimilation System. It's only focusing on the land. So I said, okay, I've been doing some geospatial watershed modeling. And I've also been working with some oceanographic parameters. How can I combine those 2 together? Okay, well, what I'll do is I'll grab monthly MODIS data sets and I will marry the 2 of them together. What the panel 4, you would call it, is meant to indicate is kind of one of the potential pitfalls when you go and marry land and ocean data together. You'll notice that like some of this dynamic stuff going on in panel 1 and the surface flow is lost when you add sea surface temperature, and that's just because you're considering it at 1 scale. So to combat that, more for visualization purposes, for us to understand what's going on, I go and split it into 2. So you can see now we have a completely unified data set. The really nice thing about that is that when you use a neural network, at least traditional neural networks, when you go and feed data into the neural network, if you have any non-numerical values and you don't account for those, it will make your neural network explode. So as another driver behind the work was just that, trying to work with these spatial data sets that are not totally complete with data. So by marrying these 2 together, I found that I was able to, for the most part, eliminate issues with when dealing with non-numerical values. Okay, This is mainly the details about the transformation that's going on, right? So pre-processing steps, collect all the data, regrid the data, right? So the global land data assimilation system has one type of grid, 10 or 20 kilometer resolution. MODIS has 9 kilometers. I found a handy tool called XESMF, which is built on the Earth System Modeling Framework, that was able to actually regrid one into the other. And then once they're regridded together, it's easy to add them, to combine them into one daily or monthly picture or whatever. Fill the NANs if there were any NANs. My handling of NANs, I believe I would take the average of the field and fill those NANs in while making sure to hold on to them. Merging, already mentioned that. Clip to the basin if necessary. Really, for clipping here, I didn't clip so much to like a watershed, but just to a general area. Interpolating, that was done if there were any small gaps in the time series for the target data. And then Z-scoring. Z-scoring is it's a statistical tool where you take a series of values, you get the mean, you get the standard deviation, and you what they call whiten the data around 0 and 1. It's shown in the literature that whitening techniques are excellent at helping improve the training of a neural network. One can imagine that if you're looking at like all of the sea surface temperature values between 0 and 33 degrees C, and you're trying to marry that with streamflow, surface and subsurface flow, which has a completely different set of units. They're not common. They have different scales and different dynamic behavior. So by taking them both and scaling them between 0 and 1, you're able to compare the two of them together. Okay, that's all the pre-processing handling of the data. The neural net configs, like I said, it's just 4 up to 1,000 neurons in a single layer, and then what I call discern, which is a deep convolutional residual regressive neural network. It's based on some research that came out of Microsoft, a guy named Kaming He. There's a great paper that you could easily find if you looked that guy up, or if you check out one of my papers, I think I might have referenced it in maybe all of them. Configurations, I didn't just take an observation of surface and subsurface flow with sea surface temperature and compare it to the stream flow on the same day. I actually went and lagged the data, right? Because we don't want just a tool that's going to tell you, hey, we can take one and transform it to the other. We want to be able to make predictions, right? That's kind of the holy grail. Like if we knew it was going to drop 20 inches of rain tomorrow, or in 2 months from now, or 24 months from now, well, we can go and make some sort of measurable change to help improve the outcome of whoever is going to be impacted by that. So I lagged the data. I iterated between z-scored yes and no, between using sea surface temperature yes and no. I kept the number of epochs of training. It's a hyperparameter when using neural networks to 100. Just fixed that. Essentially, that's how many times you run back and forth through the data. And then I iterated through training and testing split. So if you have less training data and more testing data, hypothetically, you would see poorer results than if you're training on more of the data. So there you go. Okay, so that's what I was planning to do, and here are a handful of the results. Left-hand column, when I'm not looking at sea surface temperature or considering sea surface temperature in the experiment for the prediction of stream flow from a lag of 0 to 24 months, just all lumped together. What one should hopefully glean is that when you include sea surface temperature, the prediction of stream flow according to the Nash-Sutcliffe efficiency, which is a pretty standard run-of-the-mill hydrological metric, you get a vast improvement. So the use of sea surface temperature, when you're marrying those two data sets together and then putting it through the neural network and predicting stream flow, you get much better results. that's the whole of what we're seeing here. Lots of negative values in like the bottom left-hand corner, fewer when you go to the bottom right, top left. Okay, so let's look at that a little. Let's disaggregate the data in a different way, right? So this is just considering the Columbia Basin. Nash-Sutcliffe efficiency, again, the figure of merit that we're considering. 4 neurons on the left, all the way, which is the least complex, all the way up to the most complex. Top row is when not considering sea surface temperature. Bottom is when including sea surface temperature in the prediction. What you find is that as the network gets more complex, prediction gets better. If you looked at like the last column, you see that when using discern, both of them have the mass of their Nash-Sutcliffe efficiency values greater than 0 and close to 1. But what is kind of peculiar, what's pretty fascinating to me, I find fascinating about the research, is that by just including sea surface temperature, when you increase from a 4 neuron neural network to a 30 neuron neural network, you get, and you include sea surface temperature, all those Nash-Sutcliffe efficiency values are over 0, right? So column 2, no sea surface temperature, 30 neurons, you're in the negative. You're getting a very, very poor prediction, whether it's a lag of 0, a lag of 6 months, 12 months, all the way up to 24. And then that carries through. So again, just hammering this in. The inclusion of a oceanic variable, sea surface temperature in this instance, vastly improved the predictability and the speed at which we're able to go and predict. And then the same is true for the Yukon. Really, when you look at just column 1 and column 2, you kind of see it, right? So the Yukon with no SST, all these values are right at between -1 and 0. When you've got SST at the 4 neuron, there's a wide spread. But then as soon as you bump up to 30 neuron, you parameterize a little bit better, you're getting a vastly improved calibration and forecasting. Looking at the Columbia again, just sea surface temperature and disaggregate by lag. It doesn't, one of the things I found was it was somewhat inconclusive. It doesn't really seem to matter so much. Only looking at the 2 most complex neural networks that was used in the experiments. And I know that I'm already cruising on time here, so I want to make sure that I get through what needs to get through. And then this is, again, just another disaggregation, looking at z-scored versus non-z-scored. I didn't find, again, it was somewhat inconclusive. It didn't seem to really matter whether they were z-scored or not z-scored in this instance. Definitely a place where I could go and dig a little bit deeper. Okay, so just to back this out, revisit, to go through what are the essential research questions again, right? So the first was, what's the impact of merging ocean and land surface observations of the hydrological cycle on the prediction of streamflow modeling? Well, my conclusion was you get a dramatic improvement in not just the predictability, but the speed at which you predict. How does increasing the number of output targets impact the performance? Well, if you looked at my first manuscript, it was one for each basin. When I had the input rasters, I would have 1 stream gauge. What I found is that when we increase it to 6 or 7, in this instance, it doesn't really seem to degrade the performance. If you looked at chapter 2 of my manuscript, where it was input raster, target is a raster with many outputs. Well, the performance wasn't so great with the many inputs, many outputs, but when we back it down to few outputs instead, the performance is much better. And then how do more simple neural networks fare? As the network increases in size, performance gets better, predictability gets better, but there's definitely something to be said for by just including better data, getting a bump in performance without having to increase the complexity of the neural network. You can always get a bigger hammer to hit your nail in, but maybe you don't necessarily always need to buy $1,000 hammer when a $20 hammer will do just fine. And then what's next? I would be very interested in seeing what would happen if we swapped the SST field with another, like maybe sea level pressure or bathymetry, to see if it really matters so much that we're using sea surface temperature or that we're just using anything that is oceanic in nature when married together with surface and subsurface flow. Flood forecasting, it's a pretty big deal around here. I know y'all are probably seeing what's been going on in California. We've just been getting nailed with these 100-year events that are happening every month. So it would be, I'm personally fascinated with this idea of, can we predict the extent of a flood in a particular location with any sort of predictability, like with any sort of lag in time. And then using finer products. I constrained my research to using just one compute node. When you go and you add like 10 GPUs or something, like 100 GPUs, you can do a whole lot more. It was just a personal constraint to just use one at the time. So there you go.